similar solids, just like we had similar two-dimensional figures that we studied in our first unit, I can have a set of three-dimensional figures or solids that are also similar. True for solids, like both cones, both cylinders, both rectangular prisms, whatever you want to have, where all the corresponding lengths are proportional. The diameters are proportional. The slant heights are proportional. The base edges are proportional between the two shapes and so on. Let's see if these two figures below are similar. Are they the same type of shape? They're both what? No? Both cylinders. Okay? Both the same type of solid. Are the corresponding lengths proportional? I have two sets of lengths shown. 6-inch diameter versus a 10-inch diameter. 12-inch height versus a 20-inch height. Let's make ratios of these corresponding lengths and see if they're proportional. Let's try the two heights first. 12 to 20. What does that reduce down to? What can I divide from 12 and 20?
Don't worry, I'm doing it.
4.
4. 4 divides into 12 and 20. How many times?
3 over 5.
3 over 5. Let's see if I can do the same thing for the two diameters, 6 and 10, and produce the same ratio. 6 to 10. 6 over 10. What can I reduce that down to?
3/5.
Fifths. This is what's called, remember right from our first unit, scale factor. The first cylinder, the smaller cylinder, is just 3/5 the side lengths of the larger cylinder. Or vice versa, the larger cylinder is just all the side lengths from the first multiplied by the reciprocal, 5/3. So we were able to take that scale factor and find missing lengths for similar two-dimensional shapes in our first unit. I want to take that same scale factor, figure out the relationship for areas and volumes, since we're talking about solids here in this unit. It kind of goes back to that warm-up you just did. If I take the side lengths and I double it, what happens to the area? If I double the side lengths, the area gets bigger by a factor of the area, though, pardon. If I double the side lengths, the area gets bigger by a factor of 4, because isn't it 2 times? I double 2 side lengths by a factor of 2, so it gets bigger by a factor of 2 twice. 2 squared is 4. To find the relationship, the scale factor for the areas, I just take the same initial scale factor and square it. If the scale factor for a pair of similar solids is given by A to B, the ratio of the areas for those solids is given by A squared to B squared. Which it makes sense, because what are the units for area? Isn't it always units squared?
Yeah.
That's how I remember it. Area is all about square units, so shouldn't the scale factor for area be in terms of squares? We come back here to the same question, but now for the cube. We're talking about solids. If I double the side lengths, what did I do to the overall volume of the shape? The volume got bigger by a factor of 8, because isn't that 2 to the third? I multiplied it by 2 3 times.
Oh, yeah.
So if the scale factor between two similar solids is given by A to B, the cube of that scale factor tells us the relationship between the volumes. A cubed to B cubed would be the relationship or scale factor for the volumes. That should make sense, right? Because isn't volume measured in what units? Cubic units. Well, shouldn't the ratio for volumes also be that same cube too, because it's a three-dimensional shape? A squared to B squared is the area ratio. A cubed to B cubed is the volume ratio. Trey, I'm going to pass out something here, some practice. Could you get on Google Classroom and find the same thing? I'll be right back where to look.
Honestly, I just want to go and watch her.
There's only 9 days after school until you can for straight weekends.
Oh, yes.
9 days left until spring break. Right now?
Yeah. I don't know.
All right. Let's take a look at that practice here. Trey, I've got something that looks like this. Let me share my screen. I'll show you where to find it.
So last year I kept a count on how many days to Christmas, and I started at like day 75.
On Google Classroom, Trey, go to that same hyperdoc with all the links. This resource sheet right here.
Was there like 30 of Fridays thing? Because I didn't find this.
I didn't record Fridays.
I didn't know if that was crazy.
We just
I just
basically
did-
did a
I don't record every lesson. I just kind of record the ones that I think are probably the most important. Let's see here. Similar solids, Trey. This fella right here. That link right there.
did a worksheet and did con, and I just copied out on this map.
I just
I did a short 10-minute activity. The last 20 minutes, people were working on content. She said.
Yeah.
All right. Here's that same practice I passed out. Let's try a couple. I'm going to kind of skip around and look at a few that I thought were important. Let's practice some of these together. Let's start with number 3. We're going to try a few here in class, and your goal is to get the rest of this done with what time we have left. I'm going to kind of skip around and look at a couple that I think are important. Number 3. Are the two figures similar? And if so, state the scale factor. If they're similar, they have to fit this definition. Same type of shape, corresponding side lengths proportional. On number 3, they're both pyramids, aren't they?
pyramid.
I think pentagonal pyramids, actually, because there's 5 sides to the base there, sir. So they're the same type of shape. Let's see if the corresponding side lengths are proportional. Let's look at the base edges. The smaller pyramid has a base edge length of 18. The larger, 54. Let's do the same thing for the heights. I'll make a proportion from those. 27 for the height of the first, 81 kilometers for the height of the next. I'll start reducing those down. Hopefully they reduce down to the same thing.
They do.
What can I divide 18 and 54 both by?
2 and then
Divided by 2, that'd be 9.
over 27 and then it'd be 1/3.
Divide everything by 9.
You could do that too. You could do that too. I mean, I just like to take the long way.
Let's go to the next ratio, the ratio of the height of these two pyramids, 27 to 81.
That'd be 9 again.
Divided by 9?
It's gonna be 9 over
3
27 and
ninths. Once I divide that by 9,
1/3. Wow.
1/3. What do you think? Are they similar?
No.
Yeah. If they're similar, what's the scale factor?
They're both 1/3.
1 to 3. The lengths in the larger pyramid are just 3 times the lengths of the smaller, or vice versa. The lengths of the smaller pyramid are 1/3 the lengths of the larger.
Yeah, it says. Okay.
Let's try some more. I'm going to skip down to number 5.
Well,
Try a couple of odds here. Number 5.
it says that each pair of figures is.
Yeah, so now we know they're similar. Use the given information to find the scale factor for the figure on the left to the right. So from the left figure to the smaller figure. What are we given?
We're given the area.
We're
given the area.
surface area. Oh,
The ratio of areas We will eventually. Well, let's make sure this is reduced first, Brooklyn. Because I think I can divide some numbers from 396 and 275. If I reduce first, it's going to be easier to square root because 396 and 275 aren't perfect squares. I bet if I reduce it down, it's reducible to perfect squares. But I can take a square root out pretty easily.
You did 3.
What can I divide from 396 and 275? Let me give you a hint. Try 11. It's kind of a weird number to divide into.
That wasn't a hint. That was an
Here's a really good hint. Try 11. How many times does 11 divide into 396?
36 and then
36 here. How many times does 11 divide into 275?
2 times.
A little more than that.
2.5. That's right.
There's the ratio of areas, 36 to 25. It's like they're giving you a squared to b squared. It's like they've given us
2.5 of them as well.
the area ratio, a squared to b squared first. How do I then get back to the scale factor? Square root it.
6.
6 to 5. If I want to go backwards and take the area ratio to find the scale factor, just take square roots because the square root cancels out the square in the area ratio values. So the scale factor would be, I don't know, 6 to 5, right? I have another one I wanted to do from this page. Then we'll hook over to the back. What's different about number 8? What's been different about number 8 versus number 5 that you just did?
It is in volume, like
It's just sure. What else is different about what's been given?
that's a lot of numbers. It gave us the volume and not the surface.
Right. It gave us the volume and not the area. I need to find the scale factor if I've been given the ratio of volumes. So let's start with that. Ratio of the volume from the left to right would be 3240 to 120. How do I take the volume ratio that's been cubed and get back to the scale factor? How do I get rid of cubing something? If the square root cancels out the second power, what root cancels out the third power? Cube root or third root. Before I cube root, I bet I'll make my life easier if I can reduce this first. Let's see. I need to reduce 3240 to 120.
Do you have a hint for us? What would you reduce it by?
Well, I can probably take out the 0. This is 324 to 12. Is 12 divided into 324? What is 324 divided by 12?
27.
When I divide 12 by 12, I get 1. When I divide 324 by 12, I get 27. The volume of the larger pyramid is 27 times greater than the volume of the smaller, and vice versa. I want the scale factor. That's going to be the cube root of 27, the cube root of 1, like we said. Whether you want to use a calculator or think about it in your head, what times what times what number to the third power makes 27? 3.
And then for 1, it's just 1.
When I triple the side lengths, I take the volume, I make it 27 times larger, like we talked about on your wall. Questions from the front page?
Taylor Burke, report to the secondary office. Taylor Burke, please report to the secondary office.
Okay. Would you guys try number 9 on the back? Let's see if you know what you need to know after we talk through the front page. Number 9 has been given on the back. Flip over for a minute. Each pair of solids below are similar. Find the scale factor from from the left to the right, then take that scale factor and use it to find the ratio of areas and the ratio of volumes. How do you find the scale factor? Look at the lengths that you've been given and make ratios of them. Let's see, scale factor for number 9. We could do 100 to 80. Make your life easier. What does that reduce down to? Take a digit? 5 to 4, right? Because you can divide everything by 20. There's your scale factor. The area ratio and the volume ratio. What would the area ratio be? Yeah, that's part of the answer here, Carter. Let's take another minute. If you haven't already gotten the rest of it answered, what would the area ratio and volume ratio be? A few more seconds. Easy, nice job to finish your work. I'll get that updated online. What's the ratio of areas?
5 to, area is 25 to 6.
How'd you get that?
I figured out that the ratio was 5 to 4. Then I
Just squared it. What's 5 squared? 25. What's 4 squared? 16. We already use square units, so we square the scale factor to find the area ratio. How about the volume ratio? It's cubic units. So you take it to the third power. What's 5 to the third? 125. What's 4 to the third?
4,000.
If the side lengths, 4 to the third is 64. 4 times 4 times 4, 16 times 4. 54. If the side lengths are in a ratio of 5 to 4, the area is in a ratio of 25 to 16, and the volume is in a ratio of 125 to 60. All right, last one I want to do, then you guys can start trying some of this on your own with what's left. Number 12. This one's got a bit of stuff for us to think on here. There's a few different questions we have to answer. The scale factor between two similar figures is given. The scale factor between these two shapes is 4 to 9. I'm also given the surface area and volume of the smaller figure. What would the surface area and volume of the larger shape be? I'm given the scale factor. I'm given the area and volume of the smaller shape. What would the area and volume of the larger be? Scale factor is 4 to 9. What's the ratio of areas then? We just practiced this. What do I do to find the area ratio? Say again, Jake. Okay. How about the volume ratio? Take the original 4 to 9 to the third power. I know 4 to the third is still 64. I'm going to need a calculator now. What is 9 to the third? 729. We're definitely going to need that, as well as this next information. The surface area and volume of the smaller figures are both given. Let's use these ratios to find the surface area and volume of the larger figure. So the surface area starts off with 256. I don't know the surface area of the larger figure. But I know it's in a ratio of 16 to 81, isn't it? Here's my scale factor for the surface areas. 16 to 81 is 256 to x. Small figure to large figure ratio. Small figure surface area to large figure surface area. Similarity is all about proportion, so I set up a proportion. 16 to 81 is similar to, proportional to, 256 to x. How do you solve proportions? Okay, so take 16 times x and 81 times 256. $16x equals 20,736. Then cross them up. Then divide by 16. So the surface area of the larger shape is 1,296. What's the units? Square kilometers? Side lengths are at a scale factor of 4 to 9. I can actually use that information to find the area of the larger shape. Make another proportion to find the volume of the larger shape. What's the volume of the smaller shape?
536.
So we'll change this up for a proportion to 15362x. Small volume to large volume. What's that equal to? What ratio could I use to make my proportion complete?
14
Which is the same 64 to 729. First proportion helps us find the surface area. Second proportion is the volume ratio. Go from there. Given the smaller figure's volume, 1536 to x as 64 to 729, the ratio of volumes we made from the scale factor we were given. This is going to get kind of big. 64x for the first cross product. It's 1536. 729. A big number. 3 ones. 9, 7, and 44. Then you just divide by 64, and it's 17,496. Cubic kilometers.